Organizers of this meeting for inviting me here today. My name is Sahar Safarloo from the University of Carlos III, and the topic of my presentation is optical fiber sensors for the development of dynamo-smart shoe insoles. I've divided my presentation into four main parts, as you can see on the screen, and I will begin with the introduction. What are the gait pattern characteristics? The gait cycle can be divided into different phases with several models depending on the clinical aims. Nevertheless, one of the most adopted models consists of two main phases, including stance and swing. Here you can see the stance phase in the picture that can be divided into 5 subdivisions. It initiates with the heel strike, followed by maximal weight acceptance, flat foot, heel off, and finally toe off. Below the graph, you can see the real positions of the foot at each stage. But what are the applications of gait pattern monitoring? The gait analysis can be used for distinguishing normal and pathologic gait. For example, people with diabetic foot suffer the absence of adequate sensation, which produces changes in their walking pattern. So we can use gait analysis to determine the higher pressure areas and prevent the ulcerations. They can also be used for rehabilitation, in which sensors are more sensitive than a medical observation for changes in patients' improvement. For example, these kind of devices can be used to monitor the gait's improvement in patients with Parkinson's disease after eye movement training sessions. Another application is to evaluate the balance ability in the soccer players both before and after training sessions. This brings us to the next questions. How can we measure this plantar pressure? There is a wide range of techniques for plantar pressure sensing, such as piezoelectric, resistive, inductive, capacitive, fiber optic, and wireless sensors. In this picture, you can see some examples of electronic and fiber optic sensors. Although the electronic pressure sensors can be very sensitive, their behavior is usually influenced by electric and magnetic fields. So in this study, we focused on fiber optic sensors, which are well known for their precise force measurements. Fiber Bragg ratings and intensity variation sensors are commonly used among other methods, and we can divide the fiber optics into 2 categories based on the material they are made of: silica optical fibers and polymer optical fibers, or POFs. The POFs have some advantages like high strain limits, high resistance to impact and vibrations, high fracture toughness, and low precision connectors. So in this study, we use an intensity variation POF sensor due to its low cost, simplicity of execution, easiness in signal processing, and the simplicity of the signal processing. Our macroband sensor works based on 2 principles. The first one is bending loss, in which a portion of light traveling near the bending region escapes into the cladding. The relation between the bending radius and the light intensity attenuation can be expressed by this equation, provided that this factor R over R delta remains small. It means that the bending radius is much larger than the radius of the curve. This formula shows that the bend loss will increase with decreasing the bending radius. The other contributing factor is the stress optical effect. That means when an amount of stress is applied to a fiber, the refractive index will change by this expression, in which NCO is the refractive index of the quark, U11 is the stress optical coefficient, and sigma is the stress element, which can be caused by either the bending or the force applied by the foot. Let's now take a look at the experimental setup that we use for measuring and collecting data. The experimental setup includes 3 different parts. The first part is the light source, which is a red LED. The second part is the sensing element, which is an optical fiber loop positioned in parallel to the insole. And the third part is the instrumentation system, including a photodiode, a data acquisition card, and a laptop or PC, together with all the conditioning circuits. We also used a commercial resistive sensor at this part to perform simultaneous tests. The most important part of the sensing element is its intersection, in which there is a combination of bend loss and a stress optical effect. We use the sensors in these two part of the insoles because they are the high-risk areas according to the literature. In the next step, I would like to show you some part of the results. We performed simultaneous tests using the PUF sensor on top of a piezo-resistive sensor. This figure shows changes in voltage versus time when the subject stands on the sensor 3 times. The starting and finishing points of the changes are in the same positions. However, the PUF sensor exhibits higher stability and repeatability, as well as less noise in the response. In the next experiment, we validated the PUF response with a commercial force platform in a podiatry clinic. Firstly, we compared the response of sensors at toe and heel part of the insole by measuring the response of each at the same time. The second row here in this table shows the PUF response in voltage, and the third row shows the platform response in gram per cubic centimeters. The difference between heel and toe part is 55.9% according to the PUF response, and the same parameter is equal to 57.8% according to the force platform result. And the next table shows the effect of insole material on the response of sensors. In both cases, there is a similar change. As you can see, there is a similar change in sensor response when PP is replaced by EVA. These materials are the ones that podiatrists recommends to the patients. The results prove that the PUF sensor is working properly with a maximum error of 8% compared to the commercial force platform. For the calibration, we use the universal testing machine to apply force from 0 to 2 kilonewtons with a step of 100 newtons. These figures show the normalized PUF response versus load for 3 sensors of different diameters, 1, 2, and 3 centimeters respectively. The fiber response is linear over this large pressure range, and the sensitivity is equal to 0.507 kilonewtons to the -1. And we also perform sinusoidal load tests with moderate and high frequencies to create artificial walking and running patterns. These results show that the ability of sensors to take measurements at high frequencies with high repeatability. At the end, we used the sensors inside a sandal and walked with it. Here you can see our result for 3 cycles, which is similar to the one obtained with PUF sensor in a different configuration. Let me just go back to the story I told you earlier about the eye movement problems in patients with Parkinson. These parameters that you can see in the right hand, these are the crucial data to monitor the rehabilitation process in patients with Parkinson that suffer from lack of proper eye-foot coordination, and all of them can be interpreted from our result. So this is one of the potential applications of our sensor that can be used as a complementary tool together with eye tracking sensors for the patients with Parkinson. Well, now I will briefly summarize the main points. We have prepared, characterized, and calibrated a low-cost novel PUF sensor. We also validated its performance with commercial and clinical tests. For the future works, we are going to modify the design and number of sensors to conduct research with patients with a specific disease. Finally, I would like to thank everyone who helped me in this project, particularly my supervisor, Professor Carmen Vasquez. And thank you all for listening. If you have any questions, I'd be happy to answer.